Um, Good afternoon, everyone. My name is Chen, and I'm a fresh new PhD student at ETH Zurich in the AIT lab led by Professor Ottmar Hediges. And my presentation today is about high-fidelity Mr. Me, lightweight capture personalized neuroanimatable avatars. Let me start with right away with a motivating example. Just consider the immersive telepresence, where we need a personalized visual copy of oneself to let ourselves really engage into the virtual environment. However, most of the current techniques require high-end or expensive multi-view camera rig and tons of manual efforts for the post or the pre-processing steps. In other words, there are few means for us to capture the 3D geometry of individuals with just consumer-level infrastructure, and preventing these human capture techniques being deployed into more real-life applications. So what is needed is a paradigm shift into how we can model or reconstruct human avatars from cheap but also unstructured observations with consumer-grade devices. For example, here, a single RGBD camera. And to this end, we propose a method called PINA to learn personalized implicit neural avatars from a single RGBD video sequence. And this allows us to create a detailed and personalized reconstruction of ourselves, which can be animated with realistic clothing deformations. This is a joint work with Zijian, Jie, Xu, Andreas, and Ottmar. And now this paper has been accepted to CVPR this year. Then, first of all, we define our problem. In this task, our input is a single RGBD sequence. And from this sequence, we learn a continuous implicit surface shape and a scaling field to create a detailed and personalized visual copy, even for non-expert users. The final avatar can be animated with realistic clothing deformations under predefined control poses. And you can also see that there are quite pose-dependent realistic clothing deformation during the animation. Let me introduce our method. Learning an avatar in this setting is quite challenging, since there are only a few depth frames that we can learn from, and since the depth observations are noisy as well incomplete. To solve this, we propose a method to fuse partial depth maps from the whole sequence into one single consistent representation. Specifically, we define an implicit sign distance field and a deformation field in canonic space to represent the shape and non-rigid deformation of the avatar. This representation is learned entirely from the partial point clouds. We first sample 3D points in deformed space. Both points are on and off the body surface are sampled. Given poses derived from our RGBD sequences, the corresponding canonic points can be calculated via iterative root correspondence search. We condition our SDF network on the pose so that it can learn to handle pose-dependent deformations. And we then estimate the SDF value and the normals of these points in canonic space, and then map them into our deformed space via linear plane scanning. Last, we compare these predictions with input observations and jointly optimize the pose, shape, and scaling parameters to learn PINA. More specifically, the final loss function consists of the following energy terms: the on-surface loss, off-surface loss, and the iconal loss. On-surface loss includes the on-surface SDF loss and the normal loss. On-surface SDF loss satisfies a surface supervision where the SDF values of these on-surface points should be equal to 0. And the normal loss can enforce the estimated surface normal to align with the normals that are calculated from our raw point cloud, which helps to better recover the surface details. Off-surface loss regularizes the SDF field of the space that is far away from the human body surface by using a simple mesh as a proxy shape. This loss term serves as a pseudo-ground truth to force plausible off-surface SDF values. We leverage the iconal loss to force the shape network to satisfy the iconal equation in canonic space. And with this learned representation, we can generate animations of the avatar in normal ensemble poses. Here we will show some of our results, and all avatars have been learned from real RGBD camera. Because our method does not rely on any data-driven priors, so it can handle arbitrary garment styles. Here we demonstrate the ability of our method to reconstruct even uncommon clothing. Notice that even when we pose to a very different sequence, the avatar displays realistic clothing deformations. And this generalization to new poses is independent of the subject or garment. We also demonstrate our algorithm can generalize to different human shapes. For example, the height of this man is more than 190 centimeters. Finally, our model can capture fine details, and even those that are difficult to capture from most depth sensors, such as the hair of this female subject. While our model produces plausible animations of the avatar, we leave the full treatment of the hair animation for future work. Now we show some of our ablation studies of our modules, and also the comparisons to other state-of-the-art methods. First, we ablate the benefit of our global optimization formulation. And we show that jointly optimizing the shape and pose leads to more faithful geometry. Next, we show the effects of our deformation model. Without the learned scaling weights, the deformed regions can be quite noisy and display visible artifacts. Without the pose features, the shape network cannot represent the pose-dependent changing surface details of the blazer. Here we show our comparison to other methods as the existing state-of-the-art methods for the task of avatar animation. Here we present a diverse set of reconstructed avatars from our single RGBD camera. Finally, I hope to discuss some of our limitations and also expectations about the potential future research directions. First of all, handling loose clothing will be an interesting future direction to explore. Currently, the artifacts sometimes appear on the loose part due to large topological changes during animation. This is because that the loose part, for example, the overcoat, and the deformation is not purely skeleton-driven, but also from the local deformations. And this situation will be even worse when people wear dresses or skirts. Texture include plenty for person-specific information, but for now, our avatar is textureless, and this is due to the fact we only learn the avatar from noise depth images, and without averaging any information from our informative RGB images. And as a follow-up, we remove the dependencies of our method on the depth information, where we try to learn such a neural avatar from just one single RGB camera. By combining our method current framework with implicit ray tracing technique, we are able to find the intersected points lying on the implicit surface. And similar to what we have done in PINA, we can find the corresponding canonical points of the intersected point and query the SDF values as well as the scaling weight. Then we map the point into the deformed space and phase the point to a texture network to obtain the estimated RGB value. And by comparing our predicted texture result with the observed images, we built this end-to-end trainable pipeline to learn a human avatar from only a molecular RGB video. Here we show just one toy example that we have tested on a synthetic video sequence. This sequence is from raw texture 3D scans we rendered. And has a 3D geometry output in the canonic space as well as in the pose space. Followed is our texture result. You can find on the left-hand side. Compared to the input images on the right-hand side, our method can better recover reasonably plausible fine texture details. And that's all for my presentation. Thank you for your attention, and I'm happy to discuss if there is any question.